Small stones projected with speed 65 meters per second from point O at the top of a vertical cliff, as shown on the diagram. Point O is 17 meters vertically above the point N, ends on horizontal ground, and the stones projected at an angle alpha above the horizontal where tan alpha is 5/12. Hits the ground at A, and it's modeled as a particle freely moving under gravity, and the acceleration due to gravity is going to be 10, not 9.8 in this question. We need to use 10. Let's just write down the tan. So tan alpha is 5/12. Just write it down here. And we're asked for the time taken for the stone to travel from O to A. So I'm going to be using SUVAT here. And first up, I'm just going to look at it in the vertical direction. One thing I'm also going to just prepare is using that tan alpha. So I can draw a separate little triangle over here. This will be 5, this will be 12. I can use Pythagoras to get 13. It's your Pythagorean triple. And then sine alpha will be 5/13, and cos alpha will be 12/13. So if my particle's moving from O to A, in the vertical direction, it's actually moving down by 70. So S is going to be minus 70. I'm considering up to be positive. U is then going to be 65 sine alpha, because I'm splitting it into its components. This part here is the adjacent. That's my horizontal part. That would be 65 cos alpha. I want the vertical part. So that's 65 times 5/13. It's actually going to be 25. Because I divide by 13, which gives me 5, and then I times by 5. A is then minus 10. And actually, that's everything we need. We can use S equals UT plus a half AT squared minus 70 is going to equal 25t minus 5t squared. So 5t squared minus 25t minus 7t is equal to 0. I like to make it so the coefficient of the t squared is positive. You can either put this in your calculator, or in this case, it will quite nicely factorize. Let's divide through by 5, and we get t minus 7 t plus 2 equals 0. So t is minus 2 or 7. Reject that one. Our answer is that's going to take 7 seconds. Find the speed of the stone at the instant just before it hits the ground at A. So we can see initially that it's going at this angle, alpha, at 65. And then, like here, for example, it's momentarily going to be going horizontal. And it's going to start going still to the right and down. And then at A, it's going to be going like this. This is going to be the speed at A. So we can split it again into a vertical and a horizontal component. Now, the horizontal component is actually very, very quick because it maintains the same horizontal component throughout. So basically, I just need to do 65 cos alpha. So let's look at SUVAT horizontally. Because A is 0, then V is actually equal to U, and you just get, basically SUT. But we don't even need to use that. If we wanted to know the time, we could. But yeah, like I said, U is going to equal 65 cos alpha, which is 65 multiplied by 12/13, which is then 60. So I've got my horizontal component, 60, and now I just need my vertical component. I've got everything ready for that from the information we had in part A. So I could, for example, use the time equaling 7, or I could use v squared equals u squared plus 2as if I wanted to avoid using that time just in case I'd made a mistake. I'm pretty confident, so I'm just going to go with it. So it's going to be v equals u plus at. We're still again doing SUVAT vertically. So v is going to equal 25, and then it'd be minus 70, which gives me minus 45. So it's going 45 in the vertical direction. And hence the speed, we can use Pythagoras. It's going to be 45 squared plus 60 squared, square rooted. Okay, you can bring the negative in if you want. We're looking at the speed, so it's not going to matter when you square it. And that gives us 75 meters per second. Speed at A. And then finally, one limitation of the model is that it ignores air resistance. This is always my go-to if I have to say, a limitation of it, but they've already said it here. We've got to give a different limitation that could affect the reliability. And there's lots of things you could say. One thing that jumps out in this case is that our value of G is not particularly accurate. Even if you went with 9.8 though, there's flaws with that. I personally actually normally write wind after air resistance. Those are always my two go-tos, but um, there's other options. So yeah, approximate value of G has been used. The dimensions of the stone could affect its motion, spin of the stone. It might not be going in like a single two-dimensional plane. Yeah, G seems to be constant. Wind effect, shape of the stone, anything like that. Well done.